Okay, are we ready to share? We're not ready to share? Well, can we share anyway? Because we need to get through this stuff. How did you go about setting up the first one? Okay, so Emily says she drew a graph. The whole table drew a graph. Okay, so we had like 270 over here. 3 hours, you drove 270 kilometers. So you drew your line from 0 to 0. Well, your distance depends on time, right? The distance I could travel depends on time. Your dependent axis is always the y, and your independent variable is time. Time is dependent on anything to you. Okay, so from there, how did you find out what your 650 and went over? Okay, you went up to 650.
We did 6 hours first.
Oh, you did 6 hours. So you knew in 6 hours you could go how far? Okay, folks, can we cut down the chatter, please? Okay, so in 6 hours you could go 540. And then how did you figure out the rest?
Then we went, like we drew the line after that, so that the line would be, we knew exactly what margin.
Okay.
I don't know when you won, but.
Then after another hour you can go how far? Another 90, which takes you to 630. And then how did you figure out what the last 20 kilometers would take?
We just went up to 650 and drew over, and then drew the line down to our.
Okay, so what was your final result?
7 and a bit.
7 and a bit. Okay. So that bit is another 20 kilometers, which might take a bit of time, right?
Less than 15. We did figure out.
10 minutes.
Okay, how do we know how much that extra 20 kilometers takes?
20 kilometers divided by 90. Or 90 kilometers divided by 20.
Okay, you can give me two different answers. So which one do you like?
90 kilometers divided by 20 kilometers divided by 90.
Why?
22 to the.
Okay, so what you're saying, if we think about this proportion, the time I take, I can go 90 kilometers in what time? 1 hour, which is how many minutes? 60 minutes. So if I knew what fraction 20 is of 90, then I can figure out what fraction x is of 60.
3 to 2.
Okay, so this is 2 over 3? No. This is 2 over 9. Okay, half of 90 is 45.
So you can do 45 and a half now, half of 45, 22.5. That's 50 minutes.
Okay, so you can do 22.5 kilometers in 15 minutes.
But that's a little bit too much. So then, I mean, if you want to get really down to a minute.
Okay, so it's less than 15 minutes. Slightly less than 15 minutes. Okay? That's an estimate. If we really wanted to figure out exactly, how could we do that? Okay, did anyone hear that? Say it one more time, Craig, really loud.
60 is 2/3 of 90, so you can just take 2/3 of 20.
60 is 2/3 of 90. Okay, so what Craig is doing, he's looking at the ratio between these two things. That if I multiply 90 by 2/3, I get 60. This is an equivalent fraction. So if I multiply 20 by 2/3, I'm having a lag problem here, I would get X. 20 times 2 is what? 40. Why are you not working? I'm having a lag issue here. Let me see if I can go over and type it. Okay, so we've got 20 times 2 divided by 3, which is 40 divided by 3, which is what? 13.3 repeating. So it's going to take approximately 13.3 minutes more. Okay? It's actually 0.333, so it's 20 seconds because it is 1/3 of a minute. It's 13 1/3, and in this case, that gives you a more accurate answer. Okay? Notice that we used all kinds of different proportional reasoning here, right? We're looking at setting up a ratio. We're looking at the ratio between the denominators. So all of this proportional reasoning is really important. Okay? Another way that you could have done this is to figure out that if I can drive 270 kilometers in 3 hours, then I'm going 90 kilometers an hour. And then you can divide 650 by 90 and you should get the same answer. Right? Right. Now, what will happen is when you divide your 650 by 90, you'll get a decimal that then you need to figure out is what part of an hour, right? So you're going to get that decimal and multiply that by 60 minutes. Okay. What about this one? What about your lemonade question? Okay, this one is a part-whole problem. So we're looking at parts in relation to the whole with this one. Okay? How could you model it? How could you figure it out? What did you do? Draw a picture, what did you do? 2 cups? Okay, so what did you put in the first cup? Okay. So there's my 200 lemon and 300 water. So there's my lemon, that's my water. And the other one you did what? 100 of water, 100 of lemon. Okay, so then how did you know which one had more?
Because I did 200 to 300 to 500 is 2, 5 is 40%, and maybe 31.
Okay, so you did part to whole, 200 to 500?
Yeah.
Okay, and you said that's 40%?
Yeah.
Okay. 3%. So the 40% lemon one is more lemony. Good. Did anyone do it differently?
To do with these things.
Do it with counters. Okay, let's grab some counters. Okay, if we do it with the counters.
Doesn't matter, like, we did part to part for that. But we still got, the first class.
How did you do it part to part? And then how did you compare them?
Well, the first one had a stronger lemon taste because there was a larger ratio of lemon juice to water.
Okay, so can you explain how you found out that that had a larger ratio?
Because I divided them.
So you divided them both? Like you divided 2 by 3 and then 1 by 2? And so for every 1 part of water, there were more parts of lemon. That works. Okay, have a look at this model. Oh, I should have made them the other way around. Okay, let's pretend red is lemon and yellow is water, but that wouldn't make sense. It should be the other way around, but I already built them this way, so just play along. Okay, so red is lemon and yellow is water. So I have 1 for every 2 parts here, and I have 2 for every 3 parts here. So Shauna said she just worked this out and divided like 2 by 3, okay, and figured that out. And so, well, then you'd get, what do you get for this?
0.667.
Okay, so 0.6 repeating really to 1, right? So for every 1 piece of water, I have 0.6 pieces of lemon. And over here, what do you get?
0.5.
You get 0.5, so for every 1 thing of water, I would have half a thing of lemon. Another way that you might do this is to make these a common denominator. So what would I turn this one into? If I turned it into 10, can I turn this into 10? No. What can I turn them both into? 3 and 5? 15. So I could make this 15 and I'd have how many red? 6. Okay, you can pull on that if you want. We're just not going to have enough space. But you can see that I would have 6 red. And over here, if I turn this into 15, how many red would I have? 5. So I'd have 5 out of 15, or 5 to 10, versus 6 out of 15, or 6 to 9, okay? So that's another way. The other way is to think about doubling this one, because now, I'm going to get rid of these. When I look at this one, now I have 2 parts lemon and 2 parts lemon. But I have less water here than I have here. This is comparing a common numerator strategy, right? It equates to a common numerator strategy. 2 to 5, okay, versus 2 to 6. 2 out of 6 is less lemon than 2 out of 5. Okay, so you can do common denominator or you can do common numerator. Okay, in this case, the common numerator strategy is actually easier to build. because you just have to double this one, and now you've got the same amount of lemon, but more water here.
For the common denominator, can you find that, does it matter if you found the common denominator of, the water, the lemon to water, or the lemon to the whole?
Normally I would do it lemon to whole, but we could do it lemon to water as well,
Okay.
right? Which is really just changing these both into something that you'd have 3 and 2, which you could change them both into 6, right?
Yeah.
But if you look at that model, what you're going to get is actually, it's interesting because what you're going to get for that, let's just build this. There's your common denominator strategy in a part to part, right? I have 6 water and 6 water. So it's very similar to the strategy we just did by making the lemon common. What you're doing is making the water common. So when I have 6 water, I only have 3 lemons here, and when I have 6 water, I have 4 lemon there. Okay? So do you see how you can equate these in lots of different ways? But the models are so useful, right? The models really help kids to see the equivalent fractions, and they have, or the equivalent ratios, and they help you to focus on what part it is that we're making equal.
Once the circles are yellow. So now the circles are yellow.
But what you can do is you can always make either the whole quantity, the whole, common. You can make 1 part common and see how it compares to the other part. Or you can make the other part common and see how that compares, right? So we can find common numerator, common denominator with the whole, or common denominator with the parts, right? And really, depending on how we write these ratios, if we had written them as the other way around, like every part water, right? We could have written this as water to lemon or water to the whole, right? Which one has more water, right? So it doesn't matter as long as you keep focused and keep your ratios consistent, right? If I wrote one as water to lemon and one as lemon to water, then I'm going to be all confused. Isn't it interesting how good you are at proportions? Didn't even know. What did you do for the pizza question?
Oh, I know what I did.
On the percent.
Can I explain?
Yes, you sure can.
I broke it down, so I divided in this one.
Okay, what did you divide?
First one I divided in half, so it'd be 11 to 6.
Okay, so 11 pizzas for every 6 kids?
Yeah.
Oh no, sorry, 11 kids for every 6 pizzas.
And then I divided the other one by 5, because I thought that would be easy.
Okay, and you divide the other one by 5, so what did you get?
It's like 5, 2 to 3.
Okay, can we say 5 and 2 fifths?
Yeah, we can.
Which is actually,
Oh yeah, 5.4.
do you know where you got the 5 and 2 fifths, or the 5.4? What's 27 divided by 5?
5.4.
Yeah. Why? 5 times 5 is?
25.
25, you have remainder. 2 over 5 is what as a decimal? 0.4, we did that one last day in class.
And then I was like, holy cow, look what I can do.
Look what you can do.
If I double the bottom one,
Ah.
everything will be out of 6. And then I'll have a good idea.
Okay, so what do you have then, Dennis?
I have 10.8. 6.
6. Okay, so he has 11 is to 6, as 10.8 is to 6. So now we need to figure out which one's bigger. What are we comparing? Kids to pizzas or pizzas to kids?
Kids.
No, kids to pizzas.
Kids pizzas.
So, which is better, 11 people sharing 6 pizzas or 10.8 people sharing 6 pizzas?
10.8.
So this class, 7B, gets slightly more pizza. That's supposed to be a B.
I did mine a different way, and I don't think I did it right, but I don't know why.
Okay, I hear two people talking at the same time.
Sorry,
You go first.
What?
Shauna, go first.
I did mine a different way, and I don't think I got it right, but I don't really know why.
You don't think you got it right, but you don't know why. Okay, let's talk about what you did then.
I divided 22 by 12 and 27 by 15. So I thought if there's 22 kids in the class and you divide 12 pizzas, I got 1.83, so I thought each person would have 1.83 pieces of pizza.
Yeah, that's fine.
But then in the end, I said that 7A got more pizza. Because when I divided 27 by 15, I got 1.8.
I think you may have made a calculation error.
Oh, okay.
Because it should be less than half. Or less, like, you got 1.8? Is that what you said? That's about right. What did you get for this one?
1.83?
So that's, yeah, I think you might have just made a calculation error, because you're basically doing the same thing Dennis is doing. So you should get 1.08. Oh no, what would you get?
I had one, yeah, I don't see it. 1.83 students sharing one pizza is.
For that one or for this one? Because you'll get the same fractions that Dennis got. You should, right? So 1 will be 11 over 6. This one reduces to 11 over 6. And if we think about what we learned last day in class, that's 1 whole and 5/6. And then we could work out what 5/6 is as a decimal. Because we could fair share it in 6 equal groups. Okay, and over here we have 27 divided by 15, which we can reduce down to 9 over 5. So I get 1 and 4/5. Which is 0.8. So this is definitely 1.8. Okay. What is 5/6 as a decimal? What is 1/6 as a decimal?
5/6 is 23. That's what I had.
Oh, I know what you're doing wrong. We have to flip them. What you're saying, what you've calculated, this is 1.83.
Yeah.
But what that is, you're calculating how many pizzas are being, like you're taking the number of kids and dividing by the number of pizzas. What you need to do is take the number of pizzas and divide by the number of kids. So you actually have to take the reciprocals of these to figure out what the difference is. Okay?
Why can't you do those that way? Because I thought then it would be like they would each get 1.8 pieces of pizza or 1.8.
No, this is 1.8 pizzas per, sorry, this is 1.8 kids per pizza. And the other one is 1.83 kids per pizza. So there's a little bit more kids. So again, that's where the question is what does the ratio represent? So the ratio you've calculated is the same one Dennis did. It's kids per pizza, not pizza per kid. So if you wanted to do it the other way, you'd have to flip your fractions, right? So let's take a look at how that would look. Okay? So if we were doing pizzas per kid, it would be 15 over 27, which reduces to 5 over 9. You good with that? Okay? And the other class, it's 12 over 22. Which reduces to 6 over 11. Now I'm going to call on Leah. Leah, did you do this way?
I did it
Yes, and then what did you do with your 9 and your 11?
I made them a common denominator.
You made them a common denominator. So what's the common denominator that you created? 99. So 5 over 9 is what over 99? 55. And 6 over 11 is what over 99? 54. Okay? So 7A gets 54 99ths of a piece. And 7B gets 55 99ths of a piece.
What grade is this question?
Grade 8.
Grade 8?
You're certified to grade 8. And if we had studied over 99 as converting fractions into decimals, you would find a really cool pattern, but we won't do that right now. I'll be here. Okay. Oop. Okay, so what's important is that we think about what we're comparing, right? It makes a difference if we're comparing pizzas to kids or kids to pizzas. Okay? So if we're comparing pizzas to kids, we actually need the smaller number gets the more pizza. Okay? But if we're comparing, what did I say? If we're comparing kids to pizzas, the smaller number gets the more pizza. If we're comparing pizzas to kids, it's a different way. Okay? Okay, so let's talk about percent. Percent is actually taught in grade 6 and 7 and a little bit in grade 8. In grade 6, we introduce the concept of what a percent is. We do a lot of work with percents in grade 7. And in grade 8, we talk about percents greater than 100. Okay? So, like we talked about last day, we can always write a fraction as a decimal or a percent. Okay? So, here is 1/5. You can see it's kind of shaded a little bit gray, although it doesn't always show up there. Okay? It is 1 out of 5 equal parts, but if I put it on a hundreds grid, it's how many out of 100? 20. And so therefore it can be 20%. Okay? If I were to write that as a decimal, how would I write that? 20 out of 100. 0.2. Okay? 0.2. Shouldn't use point. Okay? So a percent, just like a fraction, models part of a whole. So 1/4 is 25% or 0.25. Okay? One thing that can be very confusing for kids is percents that are smaller than 1. So percents between 0 and 1. Because they get confused because sometimes it's a decimal and then they think it has to be a decimal and then they think it's already the decimal, and so they'll take 0.5% and turn it into 50%. Right? And that's not the same. So 0.5% is what as a decimal? 0.005 because it's 5 thousandths. It's half of 100th, right? Which is 5 thousandths. So this would be written as 0.005 when we turn it into a decimal. Because 0.5% is 0.5 out of 100, which is 5 out of 1,000, right? If I broke these into 10 little parts, right? On one of the grids I gave you last day, it has the hundredths grids and the thousandths grids on the back, and it has like 10 little lines drawn in here. So I'd shade 5 of those 10 little lines, which is 5 thousandths. So a lot of kids get confused with percents that are less than 1, like between 0 and 1, that it can be very confusing for them. The other thing that can be confusing for kids is percents that are greater than 100, right? So, for example, my power bill for 2012 is 222% of what it was for 2011. That is not made up. That's actually true. I've been having this debate with Nova Scotia Power. Anyway, so here's my old bill, 100%. For every dollar I spent last year, I'm going to spend $2.2 this year. Here's my new bill. Okay? This is the percent increase. That is an increase of 122%. So it's 100% plus 122%, which gives us a 222% comparison. So kids sometimes get confused between the percent increase and the percent off. So the whole thing is 222% of the original, which is a 122% increase. Okay? So when we double something, that's actually a 100% increase, but it's 200% of the original. Okay? So these are ideas that we learn about in grade 8. Okay? In grade 6 and 7, we learn kind of how to model percents and what to do with them. And then in grade 8, we look at percents that are between 0 and 1 and percents that are greater than 100. So, and percentage increase and decrease and stuff like that. Okay, sometimes we'll look at percentage decrease as well. I should have thrown some in like that. Okay, seriously. There we go. All right. So, but the one thing I want you to learn today is the 1% model. Okay? And this is a model that we use to figure out how to take a percent of another number. Okay? So when I want to find 80% of B, I can use the 1% model. Okay? So if I wanted to find 15% of 80, for example, if I took 80 and evenly divided it so that 1% of each of it was on each square, what would the value of each little one of those 100 squares be? If I took 80 and I divided it so that I evenly distributed it on each of those little 100 squares, how much would go on each square? 0.8.
What do you mean? Oh, like if you divided each square into 10?
Yeah. Well, I'm really saying what is 80 divided by 100, right?
Yeah.
We're going to look at that in a second.
Are we looking at it? We're looking at it. You're jumping ahead. Out of 100, right?
Yeah, I'm going to say this whole thing represents $80. So what does each little square represent? $0.8 or 80 cents. You okay with that? Okay, so what would a row represent?
0.8 times 10.
Which is $8. Yes? What percent of the whole is that?
Sorry, how much is that?
10%. A row represents 10%. What does half a row represent? And how much would that be worth? $4. So if I put those two things together, is that 15%? A row and a half?
Yeah.
And it represents what value? $12. So what is 15% of 80?
So you don't,
12.
You don't draw any number.
Hmm?
Don't you think it would be difficult for someone to understand though? Like,
Why? Was that difficult?
It doesn't look like 12.
Why doesn't it look like 12?
It looks like 14. It's 15 out of 100.
It is 15 out of 100.
So we can just take the percent. Does it always come back to like look like the same percent?
Yeah, because that's what we're finding. We're finding 15% of 100,
Oh, okay.
or 15% of 80.
Can you do the next example?
Of course. Okay, so let's think about the next one. What would a row represent in the next one? If the whole thing is 25, what does a row represent? Or a column?
Gives you 125 divided by 100.
Well, that would be a square. What would a row represent? The whole thing is 25. What does a row represent? 10%, which would be 2.5. Why?
0.25 times 10.
Okay. So if I take a tenth of 25, it would be 2.5, right? And what then would one little square represent?
Wouldn't it be easier to figure out what one square represents first? Like,
Well, you can do it either way, right? You can do it either way.
If we're trying to understand the first one, what is one square?
Sometimes it's easier for people to divide by 10 and then to divide by 10 again. Sometimes it's easier for people to divide by 100 and then figure it out from there.
How much did you say one square represents?
So one little square, you tell me what it represents.
25 divided by 100.
It's 25 divided by 100.
So one square is 0.25.
So every little square is 25 divided by 100. And that's always how the 1% model is going to work, right?
If you,
When we find 1% of something, we always just take whatever it is and divide it by 100.
is it okay to just multiply 0.23 by 25?
No.
Okay, can you?
Why? If that's
Can you
my
prove to me
step-
that works?
Do you want to go to
Why does that work?
Well, because in the end, I have the same as what you have, because I have 5.75.
Yep. But why does it work?
But to me, when I look at the way you
You are not answering my question. Why does it work?
thank you.
Because my teacher told me.
But like when I look at the way you are doing it, it just looks like 23 out of 100.
It is 23 of them.
I know it is, but I don't like. I would be like, oh well, that's.
Can you have faith in this for a minute, and then I'll show you why yours works?
Okay. Yeah.
Okay.
Yeah.
Yes. Let's start from the beginning. I'm taking 25. And
Everyone listen!
yes, please. I'm taking 25 and I'm fair sharing it in 100 little parts because this whole is equal to 25.
And it's 100%.
It's 100%, but it's equal to 25, right? Because I'm saying the whole right now is 25.
So each square is.
Each square is 1/100th of 25, or 25 divided by 100, which we now know because we learned about decimals is what as a decimal?
1.25.
0.25, or if this is money, what is it?
Quarters.
It's quarters. Okay, so every one of those is 0.25.
So every little square.
Yeah. And I'm thinking about 23% of this. So if 100% is 25, I want to know what's 23% of that. So if I think about that, it's 2 columns and then 3 more little squares, right?
And so 2 columns is equal to 5.
Why is 2 columns equal to 5?
I get it because
It's 2.5.
Because each column is 2.5.
0.25 times 10.
Okay, so if I take quarters and I multiply them by 10, I get $2.50. So each column is 10 times 0.25,
And then 0.25
which
times.
is 2.5, right? So if I have 2 of those, that's 5. And then if I have 3 times 0.25, it's 0.75, so what's the value? 5.75.
I understand what you're saying, but I feel like my brain doesn't think that way.
Okay, and my brain was.
Drain it too.
But
3 times 25.
you might have kids whose brains do think that way.
Right, and that's fine, and like, I will be completely open to showing them this way, but what about the kids who don't think this
We're
way?
going to talk about that one in a minute.
Okay, that's all I want to know.
The 1% model is actually much more commonly taught than the strategy you use.
And that's okay with me,
So,
but I just like,
yep,
okay, that's fine.
we're just going to think about this in a different way in a minute, and then you'll see that this model is actually also a model of what you've done.
Okay.
Okay? So what we're doing is we're thinking if I fair share something by 100, then I take 23 of those 1%, right? When I fair share it by 100, I figure out what 1% is, and then I just multiply that by 23 because I need 23 of those 1%. So this is why it's called the 1% model, is you always go to, well, what would 1% be?
Can we do another example?
We sure can, because I have a whole other
But can
page.
we hold in our answers until people have time to think?
Yes, we can hold in our answers. So we're all going to quietly try this.
Is this gonna work? Yeah, can we have a chance to do the next one by ourselves?
These ones are actually easier than the other ones. The other ones were harder.
So we used to be able to really explain like the whole, like 23 times 25 divided by 100. How you get your answer.
Yeah, it is, but
Yeah.
I want them to understand that if you know what 1% is, you can find out what any other percent is, right? And then they'll develop some rules and strategies for themselves, right? And there'll be different rules and strategies depending on the model. So if I need to take 30% of 400, think about that. What is 1%? Try and figure out what 1% of 400 is.
Brad, keep your answers to yourself. I'm gonna actually. I'm trying to.
If she decks you, man, I'm telling her.
I think. Can you come here for a second?
Right there.
But that's how you do it, right? And for this one, we're just doing 1, 2, and 7. Oh. That's good.
And these are 2, if you want to.
And are you gonna take the time?
So now know what 1% is.
That's what I.
Perfect. That's exactly what it is.
That's when it says the problem with this is it's like, and they're all and then at some point,
Hey, wait, can I do this one?
according to the
Okay,
paper,
this one is.
they say no, this is right, and then that's what they do.
Each way. Then, and then, so then.
Which is why it's not, because it just
whole represents 400? 4. Carly.
4.
4. How do you know, Carly?
Because 400 divided by 100 is 4.
That's right. 400 divided by 100 is 4. So I took it, 400, and I found out that 1% of 400 is 4. So every little square is worth 4. How many of those squares do I need? 30 of them. And 30 times 4 is? Megan, 120. Good. Okay. What about the second one? 200. What's each square worth, Megan?
Each square is worth 2 because 200 divided by 100 is 2.
Okay, so 1% of 200 is 2. And I need how many percents? 17. So 17 times 2 is?
34.
34. Now the reason I like the 1% model is because it involves less multiplication of decimals.
Yeah.
We're more often working with whole numbers than decimals. Okay? The way you likely learned it was the way Sean is talking about, which is taking your percent and turning it into a decimal and then multiplying the decimal by the whole number. That works as well. Okay? So let's talk for a minute about why that works. You ready?
I'm ready.
Okay. If I'm taking 30% of 400, what is that percent as a decimal?
0.3.
How do you know that?
Because out of 100, it's
Because out of 100, it's 30 out of 100, right? Which we can write as 3/10 or 30 hundredths. Okay? So we can always take a percent and write it as a decimal or a fraction. So 30% is 30 out of 100 or 3/10. Okay? And what we're doing is we're taking 30% of something, and when we take a fraction of something, what operation do we use? Multiplication. So when we do 30% of 400, we could write it as a decimal and then multiply that. So 0.3 times 400. Okay? This will give you the same answer. I don't like this as well because this one is easier to do mentally, right? Because you have whole numbers versus decimals, and kids often mess up their decimals, especially when we're doing ones like this, where we're multiplying decimals by decimals sometimes, right? Okay? So you can choose to use either way. You need to be able to explain why either way works. The way that it is most commonly modeled in the textbooks is the 1% model because it generates more understanding than this model. This is dependent on having done a lot of work with knowing that we can convert fractions to decimals and decimals to percents and all that kind of stuff. Okay? So really we're using the notion of decimals and fractions. Yep.
In the newer textbooks that we'll have in our classrooms, are like these examples that you're going through in there? Like
It
how to do
depends
an
on the-
area model?
It depends on the series, but yeah, the models are in there. When a province orders a textbook, they have certain expectations. So, but you don't always get everything, right? Like textbook companies aren't the most welcoming people to work with, but you will find that a lot of provinces are putting up resources online. Like if you go to the Alberta Learning site, they've got lots of models and PD stuff that's there. Nova Scotia is building a website to go with their curriculum that's going to have models and kind of on-demand professional learning. So I'm going in to teach 1% model tomorrow. I can watch a short video about it or read an article about it or look through some examples about it, right? So there will be that stuff that's built in. That's part of the move towards kind of online professional learning. But yeah, you'll see these models, and you'll see them in the curriculum documents too.
I guess the reason I think that this would be difficult for kids to understand, because will they be able to like see that, or would it confuse them that you're saying one of those blocks is more than one or less than one? Because they're normally used to seeing 100 like grid like this as every block is one. And I like in my practice I started doing decimals with grade 5s, but didn't get very far. And like me and my CT kind of talked about using 100s grid and base 10 to show them, but as each, you know, with each place value, it kind of like changes. Like you use like the 10s.
It doesn't have to. You can start with the big cube as the 1, and then as you add tenths and hundreds and thousands. But
it took me a while to be able to understand. I mean, in the end, I understood how it worked, but I'm like, will they be able to understand that? Because they're normally used to seeing this in a different context.
well, they're only used to seeing what we show them. So if we keep using if the value of this is 1, or if the value of this is 10, or if the value of this is 100, then what we do is we set up like these hard and fast rules that this is 100, right? But now we're going to use it differently, and so we have to be really careful in those early grades not to set up false ideas of what those are. We're using this to represent 100 now because we're calling the little cube 1.
Yeah.
But we could call the little cube 5, and then this would represent 5 times that, or 100 times that much, so it would represent 500.
Yeah.
And when we're doing fractions and when we're doing multiplication, we need to have that sort of comparison going, because that's what's going to let kids know that I can keep dividing something into parts. Right? So now I'm going to let this be 100%. I'm going to let it be a whole. You don't do this until you've got a good, solid foundation of fractions and decimals before you do percents, right? But the problem is we teach those things as completely disconnected ideas. And if we don't make those connections clear, then that's what sets up the confusion, right? So for us, a lot of us, the connections weren't clear. We're learning those connections now. But if we teach this as a whole and know that, you know, if I use this as a way to model a fraction and I'm cutting it up into parts, you know, what's the value? And you can use things like, you know, one of the neat things they talked about in your textbook is the whole notion of Fermi problems. And it's where you go out and you cut a grid on something and you count the amount of plants, like in the grid or whatever. And then you use that to estimate the amount of plants in the whole area. So I might count like a block and another block and another block. And then I realize, oh, if I count all 5 of these blocks and they're supposed to be there, I can make an estimate and a prediction for the whole field, right? And so we can do things like that with kids that help them to see that sometimes the square represents 10 and 20 and 100, but we need to keep that open so that we're not shutting it down and telling them this is always 1. This is still 1. It's 1% of the whole, and since the whole thing is valued at, you know, 200, so each 1% would be worth 2, right? But we have to be really clear about that. We can't just all of a sudden go in and say, today this is going to represent 4, and then the next question is going to represent 2, and you have to talk about why it can be used to do that. And that's the piece that sometimes we miss. We don't give the kids kind of like the background for how we're going to use this model, and so we start using a model and expect they've caught up with us. So we need to have conversations about how we can model things, right? How can we use this to represent the whole and the parts? Okay, so now we're going to do the quick and dirty version of division.
Use like little transparencies like I had last time for those.
Yeah, you can.
Also have, if you have to put 4 of them, like you put
Yeah.
1 equals 1, but you have 4 of them stacked on top of
Yep.
them.
Yeah, you could do that. You could totally do that. Yeah. You just have to be careful that they don't start to think that that's 400% though.
Yeah,
But you can totally,
just so they can see that, okay,
Yeah.
the total is broken down.
the other thing you could do is make them a little bit bigger and say, okay, if that's 1%, I can put 4 counters on there, right? For kids who really need that concrete visual, you could actually take 400 little counters and evenly distribute them on a big hundreds grid and show that,
Point in time, they should have that
Right, but you might have kids who are really, like, not abstracting, or kids that really maybe need adaptations and IPPs, and it's okay to give that visual and let kids who need that do that visual. You could even take like little money and put like loonies on there. If this was $400, how many loonies would I put on each square? And get plastic money or whatever. Okay, let's talk a little bit about division. We know that division is kind of weird and wild. It can mean lots of different things. One of the things it can be is a set model. And it can be, I break it into, or I take B, some quantity, and break it into A groups, right? So I take 20 and break it into 5 equal groups. How much is in each group? But it can also mean I take 20, I break it into groups of 5. How much is in each group? Or how many groups do I have, right? So it has that double nature. With the area model, it's sort of like I have an area, I put it in this many rows, how much is in each row? Or I have an area, I put it in rows of this much, how many rows do I have? You can always ask those two different questions. A linear model, it would be I have a certain length, I take jumps of a certain length, how many jumps do I take? Or I take a certain number of jumps, how long is each jump, right? So we have all those different meanings of division, and we want to think about what they mean in relation to fractions. Okay? So I've kind of put the little set area linear. I only did one of the area models, but I'll tell you how to do the other one. So I want you to think about what we did when we were first doing division, okay, with fractions. We would take a set and make sets from it. So when I have 3/4, you see that I have 3 little red pieces here that are 3/4 of the pink. So that's how I'm modeling 3/4. And I want to make sets of 1/2. So my question could be read is, with 3/4, how many sets of 1/2 can I make? And a nice way to think of this is, if I have 3/4 of a cup of sugar, how many 1/2 cups of sugar can I make, right? Some people like to think of a concrete example. So in this case, a yellow represents a half, right? Because the pink is 1. So I can use 2 reds to make 1 whole set of a half, and then I can use 1 red to make another half a set. So my answer is 1.5 or 3/2. Are you okay with that? Okay, so that's the model we did. But there's another way to think about this. The other way is to think, if 3/4 is half of the set, what's the whole set? And this is using a proportional model. Okay? This is saying that 3/4, because I can write 3/4, well, I can sort of write 3/4.
Does this work though, like if the numbers are nice numbers to work with?
Well, we use nice numbers to develop the rules so that we understand why they work, and then we use rules with unnice numbers. Yeah. But, I mean, it will work, yes. Let's just see if I can get this to come back up here so I can. Okay? When I think about 3/4 divided by a half, I could write that as 3/4 over 1/2, right? That would be the same thing. 3/4 divided by a half is the same as 3/4. Come on, be nice. These two things both mean the same thing, right? 3/4 divided by half. So I could think of this as this is something over 1. I could find an equivalent fraction that is equivalent to the proportion of those two fractions, right? We just did proportional reasoning. So if 3/4 is half of a set, what's the whole set? 1.5. Or what's another way to say it? How many quarters do we have?
4.
6 quarters or 1 whole and a half. Okay? So you get the same answer. And what did we do there to make that equivalent fraction? What do I multiply a half by to get 1? 2. So what do I need to multiply the 3/4 by? 2. Oh, so it's almost like I multiplied by the reciprocal and got the answer. Oh, no, wait, that's exactly what I did. Okay, let's look at this one. Linear model. When I'm doing the linear model, I'm jumping, I have 3/4 of a length, and I want to measure off lengths that are 1/2. I can measure a whole one and half of another one, right? So if I wanted to use lengths of a half, or jumps of a half to get to 3/4, I would use 1 whole one and then half of another one, and then I'd be at 3/4. Okay? Very similar to what we did here, it's just a linear model. I can still think of it the same way if half of a jump is 3/4, and you can think 3/4 of a meter if you need to put a context there, right? Half of a jump is 3/4 of a meter. What's the whole jump?
3/4.
Twice as much as that. So it's 6/4 or 1.5. Okay? Now here's my favorite model, and don't ask me why, I just love it. Because, you know, I have an affinity for the area model. We get along well, me and the area model. We're happy together. So, I want you to imagine that this was a sheet of paper, and I folded it into quarters, and I shaded 3 of them. You okay with that?
Yeah.
But what I said to myself is I want one of the dimensions, right now the dimensions are 1 by 3/4, because the height of this square is 1, because it was a unit square. So it was 1 by 1. Now it's 1 by 3/4, the shaded part. We're good? Okay? But I don't want my height to be 1. I want my height to be 1/2, right? When I have area model, I can set one of the dimensions to be the divisor and figure out what the other dimension is, right? If I had 12 as my area and I divided by 3, that can mean make your height 3, what's your length, right? To get 12 as an area. Okay, well, it's because we haven't finished yet. And that table over there is chatting. Right, Craig? No, there we go. Okay. Let's all listen so we understand this model. Okay? This area is 1. Remember when we were doing multiplying fractions and we were folding paper? So this area is 1. Disregard this line for a minute. Each column is 1/4. And I've shaded 3 of these. So if I think about this sort of little piece right here, this is 3/4 of the whole square. Okay, here's my whole square. This is 3/4 of the square. We good? Okay, the dimensions of this shaded area are height of 1, width of 3/4. Right? It's 3/4 by 1. But I don't want it to be a height of 1. I want it to be a height of a half. So what would I need to do? Cut it in half. Right? But I want to keep my area the same, so I need to pick up these 3 little pieces and move them down here. What's the width of this? 3/4. Right? Now the height is a half, and I have 3/4 and 3/4. So I have 2 sets of 3/4, which gives me a length of 6/4 or 1.5. And that's how you look at it with the area model.
I'm not sure why you would ever move that piece like that. What does that do?
Because you want to preserve area. So
So you want to make it.
okay, wait.
Why do you do that?
Hang on. you are creating something that has to have an area of 3/4 of a square meter, and one wall has to be 1/2 of a meter. My area has to be 3/4 of a square meter, or 0.75 square meters. And I want the height to be 1/2 meter. What does the length have to be? Okay, watch me do this. I have folded a piece of paper that is 1 by 1. Would you all agree that this area now represents 3/4 of what I had originally? This shaded cake area, see?
Yes.
Okay, I'm gonna get rid of this because I don't need it. It's gone. This is 3/4. Let's pretend it's square centimeters. So this is 3/4 of, or let's pretend it's square decimeters. 3/4 of a decimeter squared. Okay? Now I want to have this area, but it's carpeting. And I want to fit it in along the wall that's only 1/2 a decimeter. So I need to still use all my carpet, but make my height 1/2. What's my length? 3/4 plus 3/4 is 6/4, which is 1 1/2. Okay, so it's forcing one of the dimensions to stay the same. Now watch this, just for the sake of, parlor tricks. Suppose I wanted to, I need an assistant, sir. Here, hold those two pieces right there. Suppose I wanted instead to take my 3/4 and make width 1/2. Okay, what would the other dimension be? Okay, Sarah, can you fit those up here so that now? There we go. The area preserved. Have we changed the area? Have we lost anything? What's the height now? 1 and 1/2. Either way, when I change this dimension to 1/2, I still get 1 1/2 of the other dimension. Okay? So I could have just as easily cut these two pieces off and stack them up here to show that the area is preserved. What's the other dimension? Okay, so those are models that we can use for division of fractions. I've left you some you can practice. We're not going to go over them next day in class, but if you want to share them with me, I will tell you if you have these, I'll take them. If you've asked me for more time, I'll take them later. Okay, row is 1/3. Right hand sets of 2 fails. This would be 2 fails. Just a second. Let me draw it for you.